Welcome, listeners. Thanks for listening to the very first episode of the Semi-Doped podcast. I'm Austin Lyons. I write a Substack called Chipstrat, and with me is Vic, who writes Vic's newsletter.
Hey, Austin. Yeah, I really love the name for this podcast. I hope we continue to love it like 5 episodes in. By the way, for listeners who are not familiar, my name is Vikram Shekhar, and I write a Substack called Vic's Newsletter. We write so much semiconductor content between Austin and myself that we decided we should just talk about it on a podcast. And so here we are. All right. So we should talk about what's on everybody's mind right now. Nvidia decided to drop a whole lot of coin to buy a company called Groq. And pretty much everybody online lost their mind about the sheer size of this deal and what it means really for Nvidia. Like, there was so much narrative about, oh, HBM is going to be affected. Oh, GPUs are dead. This is the new thing. We are in the age of inferencing. SRAM is what it's all about. Anyway, there was so much noise that I spent so much time reading all these threads and figured, I think we should kind of sit down and have a little chat on what's going on here and kind of break down some of the more technical and business aspects of what's going on here and maybe give some more context. What do you think?
Yep, that sounds great. Let's talk Groq. So for listeners, this is Groq with a Q, the chip company. And yes, the news dropped. It was Christmas Eve. And it felt like that was strategic. Like, it was surprising, and Groq had an announcement, and Nvidia didn't really say anything. And then everyone signed off for the holidays. And so I think that also helped lead to a lot of speculation, amongst us who track the industry closely. And so, yeah, it was what we read. At first, I actually read it as it was an acquisition. And then quickly people came and pointed out and said, no, this is a $20 billion deal that NVIDIA is doing where they are acquiring a non-exclusive licensing agreement of Groq's assets for $20 billion. And I think Groq's announcement said, CEO Jonathan Ross and the CTO Sonny Madra, or whatever his title is, will be going to NVIDIA as well as many key employees. And so I think right away, I was first a little bit like, oh, is this just like the leadership going over? But then I think later there were reports that actually it's like most of the company is going. But right off the bat, it was a little surprising in that, like, oh, this is not an acquisition. This is more of this like newfangled pseudo acquisition that we've seen with AI labs. Did you have a take when you saw that news?
Yeah, so I was actually disappointed when I saw that it was kind of an acqui-hire kind of deal initially, or at least what I thought it was, because I think it sets a really bad precedent for startups in the Bay Area or anywhere really. Because if they only were to hire the key executives or the key brains behind the project and not really take the whole team with them and just pick the brains and the technology, then there is really no incentive for anybody to work at startups anymore, because everybody knows the payout is going to go to the top, 2-3 employees, and nobody else is going to get anything out of it. But I'm happy, like you mentioned later, even I found out that it's not like that, and they did right by the employees of Groq. So this is a good precedent. I'm actually happy with the way things turned out in a sense.
Yeah, totally. It did have a happy ending. And I have seen now there's talk where lots of people are saying, hey, we should make sure that this gets codified somehow, that companies can't come in and sort of like raid the executives and the IP, and the employees are left with options that they were promised. And that's part of the comp package for startup employees, is this idea that your options could be worth $1 billion someday. And if that can't manifest, then it does sort of break the whole premise of startups in the first place. So yes, I was happy to read that Jensen did right by the Groq employees.
Why do you think that the whole narrative came about after the acquisition, or rather acqui-hire or whatever it is, that GPUs are dead? Why did we get there?
I think that zooming out and looking back in 2025, the narrative like coming into 2025 was really about like GPUs versus XPUs, and is Broadcom and their hyperscalers going to eat Nvidia's lunch? And so there's a lot of pushback about like, no, GPUs are really flexible, and XPUs like, you know, where are they? You know, Google's got a roadmap and they've shipped 7, generations, but at the time we had barely seen Trainium 2, and I don't know a Maya from Microsoft. That just seems like a design on paper. And so it was a lot, the pendulum was in GPU's favor and a lot of people pushing back on XPUs. I think throughout 2025, then there was starting to be a lot of talk about TPUs, especially with like Google potentially selling TPUs to others, and the pendulum started swinging a lot. There was a lot of narrative and conversation around TPUs, and so it felt like sort of a GPUs versus TPUs dance. And meanwhile, at AWS reInvent, there was talk about Trainium 3, and so again, kind of TPUs and XPUs were a thing. Now, of course, all of these use HBM, and so then it is a little interesting that here at the tail end, all of a sudden LPUs slid in, and everyone's like, HBM is dead.
But the thing with LPUs, which is Groq's solution, and why everybody declared HBM dead when this acquisition news showed up, is because it uses SRAM instead of HBM. And SRAM is actually so much faster than HBM is, even though it's actually high bandwidth memory. SRAM is actually faster. The only problem with SRAM is that its capacity is highly limited. So the question immediately comes up is, GPUs are great, and HBM is highly supply constrained, and it requires chip on wafer on substrate packaging from TSMC, which is very hard to get and is also highly supply constrained. And I think that I read in the news that several Google executives were affected by the fact that they could not get sufficient HBM procurements on time. So it's like a serious matter, this thing. So the SRAM solution from Groq provides an entirely different alternative universe, because you don't have to deal with HBM, because HBM is only made by 3 companies: SK Hynix, Samsung, and Micron. Did I get that right?
Yes.
And SRAM is actually made on logic chips, so TSMC could make it. There's no need of all this fancy packaging, and you don't have to package it, try to stack DRAM die or package it on a CoWoS interposer or any such thing. So it like takes out so many capacity bottlenecks from using HBM. And so that's why it seemed to everybody that, oh wow, this is a solution that breaks all barriers and it could take over. The main problem lies in the fact that it does not have capacity. So if you were to run a Kimi K2 model, you're going to need 1 terabyte of memory to run that model, even for inferencing. And that is simply not possible with SRAM-based chips like Groq LPUs, because you're going to need a lot of them, because each Groq chip has 230 megabytes of SRAM. So you can imagine how many chips you would need to run 1 terabyte requirements of memory. So that introduces a whole dimension of complexity, because now you will be bottlenecked by how the networking between so many GPUs work and how the interconnect bandwidth and limitations start to show up in the big array. So it's not as simple that just because you have SRAM basis that you can just substitute HBM and take over everything, right?
Totally. And you make a good point. And I think the framing that leads to all this is not HBM versus SRAM, because I think people who aren't quite as close forget that every chip uses SRAM for local storage, for cache, right? CPUs, GPUs, LPUs, TPUs, whatever. But it is HBM versus no HBM. And so, yeah, Groq's LPUs don't have HBM. And so to your point, that's like the key insight, which is no HBM means no capacity constraints like CoWoS and HBM constraints. Totally. But of course, you point out, yes, but there's a trade-off. SRAM, it takes up a lot of die area and thus is expensive. It's very fast. It's very local to the compute, very fast. But with only, to your point, 230 megabytes per chip, you're talking like tying together thousands of chips to run a really large model, and even, several hundred, 500, 600 to run a smaller or mid-sized model. And so then that's definitely the trade-off. Now, if you've got hundreds of chips, you have to ask, how are we tying all these together, shuttling all the data around? And of course, what is the power cost of all of those chips? What is the real estate cost of all of those chips? Right. And so, of course, the economic cost might be a lot less because, by the way, one might ask, well, why did they only have 230 megabytes of essentially SRAM on these chips? And you have to remember that this chip was designed many years ago, I think 2020, on like 14 nanometer technology, and this essentially was designed prior to Chat GPT exploding. I mean, transformers were a thing, but I don't think that they were probably necessarily designing this chip with these really large language models in mind, which is how we end up in a place where you have to tie hundreds of them together to run today's large language models. Now, back to real quick, going back, so again, in all of the narrative, some of the nice things, not only do you not have the HBM constraints and the cost constraints, it's on 14 nanometer technology. So surely these chips are cheap. So there is the whole like, well, yeah, you need hundreds of them, but they're probably way cheaper than buying a GPU. But yeah, let me pause there and ask you. So going back to LPUs, so we know they're cheap, but we know the trade-off is they don't have much memory. Do they have any other benefits using
Yeah,
LPUs?
yeah. LPUs are an interesting architecture. Actually, it is substantially different that we should talk about this for just a minute because GPUs are, graphics processing is what they've been used for, but they're very general purpose. You can do a lot of stuff with GPUs. You can, do ray tracing or whatever. You can do AI with it. It's all about how you program this thing and it does whatever you want it to. LPUs are actually quite different because they are like a finely tuned machine. And an analogy I really like is that they're like a factory where every worker's movement is coordinated to the last millisecond before their shift starts. So that whenever the product has to run through that factory, there is almost no wasted time, motion, energy that uh, is used to push the product through the factory line. So that's kind of the basis behind what LPUs actually do. So they fundamentally work based on what is called a very large instruction word, or VLIW. And this is so unique that actually I should take that back. It's not, it has been around a long time, but its context in inferencing is important to understand because typically how processors work is that when you give it an instruction and say, hey, go and compute this for me, what it does is it takes the instruction and the hardware decides, okay, what instructions need to be executed first? Do I need to make the multiplications first? Then do I need to add them? So that means, wait, the multiplication should be done before I can add them together. So the sequence has to go this way. And then I can probably take this and load this into memory. And so it decides all this at runtime. So this is how general processing works, in GPUs and things like that. And the very long instruction word approach by Groq kind of flips the whole argument. So nothing is done at the hardware level. Everything is decided beforehand. So what that means is that you have to take a bunch of these operations. So if you're going to do the addition, if you're going to do the multiplication, if you're going to load it in memory or store it somewhere else, everything has to be defined beforehand. And you have to specify it exactly, and the hardware is just dumb. It just does exactly what you tell it to do, right? So this is very difficult. So think about that. Not only do you have to uh, orchestrate hundreds or thousands of these uh, Groq chips, but you also have to be very specific about how the instructions are executed on this thing. So that makes it very, very difficult for people to write code to it, and it is actually a compiler nightmare because it is so complex because everything has to be decided beforehand. One analogy to this is Actually, before that, I should explain another thing. There's another benefit to LPUs, and that is that it is very deterministic. And it kind of falls
Hmm.
out of the process of predetermining what has to be done well in advance, right? Because if a compiler, if the instructions have to be decoded, what actually happens is uh, it has to determine when it's going to access the cache, if the data is available in the cache or it misses the cache. So there's a lot of variability in how general processing works. But with Groq's VLIW approach, it is fixed because the whole orchestration, the choreographing of all the instructions are done beforehand, right? So you can exactly count to how many clock cycles certain instructions will take. So that makes it very deterministic, right?
Hmm.
I'm going to give one last analogy to explain how determinism works here. Because let's say I'm giving you, Austin, instructions to go to a restaurant in, let's say, San Francisco. So I'm going to tell you, hey, Austin, just go down to Union Square, go 4 blocks east, you'll find a gas station, and diagonally opposite from the gas station is going to be this restaurant I'm talking about. So what it requires you to do is first you need to think about how do I get to Union Square? And then wait, then I have to go what? How many blocks east? And then you need to find the gas station, and then you're going to find the destination, right? The Groq approach to doing that would be I'm going to give you the GPS coordinates to Union Square, and then I'm going to tell you exactly how many meters you're going to go from there in a given direction, and at what angle from that destination point the restaurant is at, right? So this makes it very difficult to program things like this. So although it has its benefits in terms of very low latency because nothing is determined on the fly, it's all predetermined, and you know exactly how long it's going to take. So this has important use cases which we should talk about actually.
Yeah, definitely, definitely. Let me summarize it for listeners. So, Groq's LPU, architecturally, it takes the complexity and moves it from hardware into software. So the hardware is very simple, no scheduling. Like a CPU, for example, anyone who took a CPU architecture course would remember like out of order scheduling and execution, right? The hardware might just look at the instructions and schedule them differently to try to optimize on the fly. And what you're saying is that with an LPU, the hardware is very simple. All of that scheduling is done in software by the compiler. It takes a look at the program, decides how to order everything, and then gives precise instructions such that when anything is running on the LPU, everything is known. And that's why it's called deterministic. Like we know exactly where the data is and how long it's going to take to flow through and when it's going to come out the other side. And so an LPU has ultra low latency, it's deterministic, and the determinism comes from how the architecture is built and designed. And then the ultra low latency is just like everything's running. There's computation and then there's accessing memory, and the memory is SRAM. It's fast and it's close to the compute. And then the determinism is just where everything is going to be. Now GPUs are more general. Now I will say with data center kind of cloud GPUs, obviously they're not being used for graphics anymore, and some of that's stripped out, and they're definitely tuned for AI. You can think of them as AI ASICs in a sense. Even like with every new generation of Nvidia GPU, they tune it specifically for AI workloads. For example, spending more compute area and die area on lower precision, like FP8, FP16, and not spending as much on FP64, right? So they are making architectural decisions that are tuned for AI, but at the end of the day, it's still general enough that if you want to run all sorts of programs and with different quantization, like it can handle it. And so there's some trade-offs just on the way they're designed. LPU, deterministic, ultra low latency versus GPU flexibility, dev friendly, of course. And we can get into that of some of the trade-offs of the LPU. But let me hand it back over to you to keep going.
Yeah, so now we have established that LPUs cannot hold large models because it is SRAM based and SRAM does not have that capacity. SRAM has stopped scaling quite a few generations ago. Maybe we'll see small improvements as we have gate all around. We have a little bit improvement from there. Maybe as we go to complementary FETs, we'll see more. But essentially, SRAM doesn't get any denser. And therefore, it's going to be expensive to begin with. So you just can't stack SRAM the way you do HBM. There are many reasons for that. Maybe we shouldn't, get into all those reasons right now, but fundamentally it's limited in capacity. You cannot run big models, whereas you can run really big models with HBM. And that has implications on what kind of use cases HBM-based inferencing can do and what SRAM-based inferencing can do, right?
Yes.
So I'm gonna ask you, because I really liked your article on Substack where you referred to hyperspeed inferencing using Groq and SRAM, which is a very important use case that we do need. So it's not always about serving the large mixture of expert models that we use day to day nowadays. There are so many applications that require just small models. So I'll let you explain some of these awesome applications you had in your article.
Sure. Yes. So yeah, I coined Groq's LPU like a hyperspeed machine or focused on hyperspeed work cases, which is if you go to think about it, okay, I've got this LPU, it doesn't have much memory, so it can only hold a small model. What are use cases where this still matters? And of course, it's use cases where latency matters a ton and the model just has to be good enough. And so you can think of something like serving ad copy. And, Google actually already does this with their TPUs. But historically, when you serve ads, it's a person searches for a thing and then you try to match the keywords and then give them an ad that kind of matches it. But it's not necessarily, the ad copy itself is not necessarily hyper personalized to you. That being said, with LLMs, it becomes very easy to, in natural language, like know about me, know that I should see this ad, and actually write the ad in such a way that speaks specifically to me, Austin Lyons, given where I live or what I'm really interested in. But of course, at the end of the day, like Google, a search engine's all about responding as fast as possible. So if you're going to hyper personalize it, that's going to improve like the ad click-through rate. But it can't come at the cost of being much slower. So that's a perfect example where like, hey, maybe something like Groq could have just a small model, but it's good enough to write some plain English to hyper personalize this ad for me, but do it crazy fast. So that was one that came to mind. Of course, you can think of lots of other use cases. I think even routing between models used to be, of course, there was that terrible user experience on ChatGPT where you had to know enough to say, yes, I want the slow thinking model or the fast, just respond right away model. In an ideal world, the user wouldn't have to take on that burden and the application would just know which model to route it to. And obviously now ChatGPT does that with 5.1, 5.2. Generally how they do that is they just take a peek at what you're asking really quick and then decide like, oh, I should probably think about this, or no, I can respond very quickly to this. That's another example of a model that's small, but just needs to respond really quickly and then could actually just forward it on to a different, bigger model or a huge complex model, or even like your video generation model or your image generation model or whatever. So I think routing between models is another one. And then, of course, agents is an interesting one because agents, now we're talking about if you give a task to an agent, it might run inference not once, but like hundreds of times, like as it loops through deciding like, okay, I did this, I did this, I did that. What's tricky is you want like the smartest agent you can usually for those because you're like, I'm entrusting you with some work and I want to walk away and come back a few minutes later and you've made progress. But what would be interesting to ask is, are there ways that an agent could still have access to a fast model, or are there certain use cases where most of what the agent's doing is simple enough? Like, could it all run on this like ultra low latency? And so, I can definitely see a world where an agent, maybe it has like tools to call different models. And at times when it knows, oh, these steps are really easy, could it call out to a model that's running on like some hyperspeed hardware, like a Groq LPU? So I'll just pause there, but those are a couple examples where latency matters most. At the end of the day, it's anything that a human's interacting with and needs a real time response. That's where something like Groq's LPU could shine.
Yeah, I like another example. I think I had another example that I read in your article, and that has to do with speaking with chat agents or doing dynamic translations where speed is everything. Like you don't
Yes,
want to talk to an LLM who's helping you out on a chat session or whatever and say something and then you don't get a response because the inferencing is slow and there's like a long time to first token and you're like, wait, did it hear me? And then you start speaking again and then it again gets a bunch of tokens and it's inferencing that. It's a bad user experience. So
totally.
anytime you have like chatbots, you need fast inferencing. It doesn't have to be super clever. It's not like you're asking it to cure cancer or something. Just you're just talking regular stuff with it, and it's good to have a fast model for something like that,
Yes.
right?
And those of course are all running on the cloud. But you mentioned in your article on your newsletter an interesting edge application.
Yeah, so this was something I came across in a Discord conversation, and one person on it uh, mentioned, "What about robotics?" And that really got me thinking because that is another application where Nvidia is pretty invested in. They have their Jetson platform, and everything that SRAM based inferencing, which Groq is capable of doing, fits that bill because it has to be really low latency because the environment changes so quickly. If you're doing physical AI, it needs to process and make decisions really quickly. So that low latency that you can get from SRAM based inferencing, really fast inferencing, is very useful. It's usually single user because the robot is only like
Mm.
doing whatever sensing stuff it does around itself. It's not like a multi-user GPT scenario here at all. And in order to respond quickly to environments, it has to respond in a deterministic time frame because you need to know that the correction has to be applied within so many clock cycles. That kind of stuff is very helpful. And these models that run on these kinds of robotic applications could be quite specialized. Because if you have a vision one, or if you have something that just drives motors based on what it's doing, all these edge applications could be very
Mm.
specialized models that don't have to be big but need to be really fast and deterministic. So it looks like the Grok application really is a good one on this.
Yeah, that's really interesting. I think of industrial robots where you need them to do a thing and you need them to do it quickly. And so, although the selling point is never determinism, it's always about, just speed to the user or to the process in an industrial setting. There is something nice about being able to talk about like tail latency and hey, we'll always be able to make a decision in this amount of time so you can plan, your factory line accordingly. That that'll be super interesting to see if this type of architecture comes to the edge.
Another application actually that really took me by surprise that when somebody mentioned it in a comment on my post is like radio access networks or AI RAN. Somebody said, "What do you think about AI RAN?" And I was like, hold on a minute. Because Nvidia just invested like $1 billion into Nokia, trying to get them to use like GPUs in RAN applications. I think I should explain what RAN is a little bit. It's basically radio access networks take all the wireless information that's from devices and stuff in the cellular tower and then process the multi-user interference-based scenarios, does manages the spectrum, all of this stuff, and then sends out all that information on the wired network, to go through the long haul networks and subsea cables or even between continents. So the first stop from all this wireless data that comes in is the radio access network. So there's a lot of decisions that need to be made based on the current environment that the cellular tower is seeing. So right now, there are custom ASICs that run these kinds of things in FPGAs, and Qualcomm is a big player in this. So Nvidia wants to somehow get into this market by introducing GPUs. The one problem with that, and I read a light reading article on this that's explained this a little bit in detail, is that Nvidia's solutions are just too power hungry. Like the
Mm.
existing incumbent solutions are like 1/10 the power of what a GPU would use. So the article described it as like outfitting a Vespa with a V8. You don't need it. Is it cool? Yeah, it's cool, but you really don't need a Vespa with a V8 engine. So you have to put something that fits the application. And interestingly, it might be that these SRAM based inferencing solutions, Groq or otherwise, may find applications there because, again, when you're talking about 5G networks or even 6G, because, I think that's the whole goal is, to make better radio access networks for 6G. The latency is a very specific number. You cannot have latencies, it has to be in the sub-millisecond latencies, which means that you can't run just a general GPU and having these kinds of pre-compiled, pre-decided instructions that just run on dumb hardware is the best way to get the lowest latency. So I'm not sure whether this is even a thing, but in thinking through this, I thought this was an interesting edge application for like SRAM-based inferencing. So I just thought I'd
Yeah,
mention it.
yeah, that's super interesting. So now I have a question to push back a little bit on this, but first let me take us back. So at the very start, we asked like, are GPUs dead? And then we've talked through like, well, no, there's just architectural differences. GPUs use HBM, so they can have large models. They're very flexible. They can be high throughput, dev friendly. Of course, they have trade-offs. They consume a lot of power. They're expensive. LPUs, ultra low latency, deterministic, only small or medium models though, because they don't, in Groq's first generation, there's barely any memory there. Barely any memory with respect to the size that LLMs need. Now, when we talk about edge applications, I think the pushback would be, okay, well, still with Groq's Gen 1 chips, even if you want to do AI RAN, like, yes, it could be a lot lower power, but can you cram 100 of those chips in an AI RAN box or 500 or whatever? And so I guess my question to you, Vic, we're speculating here, but for an LPU like architecture to come from Nvidia and Groq to the edge, do you think that's something they could do with their first generation chips? Or are we talking about taking the IP and building new offerings, new SoCs?
I am not sure what kind of resources these workloads require. Actually,
Mm,
that's a piece of information I need to really look up, because you're right. Like if there is a large memory requirement to run these loads, you need HBM again. This is not going to be the solution for it. But these are currently run by specialized DSPs. The RAN
yeah.
applications today. So they do not have that kind of large bandwidth requirements from what I can tell. So it might be more well suited to using Groq like inference solutions rather than HBM like inference solutions.
Mm,
So I think it's closer to one end than the other.
sure. Do you see a middle there where it's like, could we see a Groq like heavy SRAM, but also accesses some DDR in a use case like this?
Yeah, actually, that's kind of what D-matrix solution is, because they have on-chip SRAM, which they use for digital in-memory compute, but they also have the ability to offload KV caches and stuff to DDR, LPDDR, and their next generation chips are going to have 3D stacked DRAM
Mm,
chips. So you're going to get a much better DRAM throughput compared to LPDDR on a board if you stack chips on top of memory, because you have so much more. You have the entire surface area to put parallel lanes through. So you're going to get a much higher memory bandwidth if you stack up chips. It's not going to be as good as SRAM, maybe, I don't know, but it's going to be really good. So
mm,
yes, SRAM and HBM can work together, or HBM, SRAM and DRAM can work together too. So there are those kinds
fascinating.
of solutions, but not with Groq. Groq does not have that solution right now. It's only SRAM.
Sure. But presumably, if NVIDIA wanted to, this is all well known, and they could take work with Groq to take their IP and make some of these other offerings if they wanted.
Yes, yes, it has been done too. If you look at Intel's Ponte Vecchio, the chiplet architecture,
Hmm.
chip, they do have SRAM and then the ability to do more on DDR. So those kinds of things do exist, out there. So it's not like Nvidia cannot use the IP they just acquired to do some cool stuff with. And I think we're all waiting to see what that is.
Totally, totally. So I think probably last question or topic here, I think kind of what you're getting at from the memory angle, which is really interesting, is a spectrum of systems that make different architectural decisions with different trade-offs. Some are SRAM only on the other end of the spectrum, some are SRAM and HBM, and maybe somewhere in between it could be like SRAM and DDR, LPDDR, GDDR. Um, we've actually, which of course allows you to get different outcomes from ultra low latency, but complicated compilers to not quite as much latency, but easier for developers and high throughput flexibility. We talked about it in thinking about the context of the edge market, but we're actually seeing
Uh-huh.
this in the cloud market already. Nvidia, not only do they have, obviously they have Hopper and Blackwell, which are pretty much a little bit of one size fits all, although you could have Hopper, HGX or DGX. So there's different SKUs within there, but at the end of the day, it's the Hopper architecture, it's the Blackwell architecture, Grace Blackwell or Blackwell standalone. So there's some knobs you could turn. But now with Rubin, we've heard of Rubin CPX, which
Mm-hmm.
makes those memory trade-offs, and it's focused on prefill workload. And then we even saw Nvidia talk about using RTX Pro servers, which again make different memory architectural decisions to use for AI workloads. For example, in simulation, like in autonomy, they talk about having three computers. One is the edge autonomy computer, like NVIDIA Thor. Um, and then one is the big training computer. So that might be a Grace Blackwell, but then running simulation, like, hey, I just want to simulate this car running this intersection and all the different weather conditions I can think of. You could actually run those simulations, which involve AI, on, say, these RTX Pro 6000 servers. So I guess my point here is we're already seeing a portfolio of options from NVIDIA that have different compute, which everyone focuses on, but they also make different memory choices. Um, do you have any thoughts? Will we continue to see this? And you mentioned D-Matrix in the mix. Will we continue to see this in the cloud? Will we see this happen on the edge? What do you think?
Yeah, so there are so many applications like video generation, image generation are definitely the more compute heavy or the heavier applications of LLMs. Whereas you see, like we spoke about these lighter requirements, I don't know if it's robotics or ads being served on the fly. These are completely different applications which require actually completely different pieces of hardware. And that is what I think is emerging right now because there is no one size fits all. And throughout the history of technology, we have kind of seen that there is no one size fits all, and everybody's
Mm-hmm.
applications and needs are different. And so, what we are seeing here is an emergence of a whole variety of applications where, depending on the workload that you're going to run, data centers have to deploy the right kind of inferencing solutions to have the maximum cost benefit from running these data centers, right? And this whole Groq thing might just be that little piece that NVIDIA was missing with hyperspeed inferencing, like you call it. Maybe this just checks that box and gives them the entire uh, salad bar of inferencing options that they can now deploy anywhere they want.
Mm-hmm. Yeah, totally. That resonates with me. I was thinking of it in terms of like it increases their portfolio's surface area,
Right.
and agreed with you that as we continue to progress with enterprises actually adopting AI, figuring out where it fits, figuring out where interesting use cases might be on the edge, that at the end of the day, it is always about TCO. and it's about that cost benefit. And that's where it gets back to sometimes you only need a good enough model. A small model might work, but it has to be super fast. And so I think probably to wrap up this episode, that's our takeaway is the LPU is different than a GPU. Both are super useful and they serve different use cases. So HBM is not dead, GPUs are not dead. And
Agree.
Nvidia seems to know what they're doing here.
Yeah, and I think a lot of people have been trying to find the grand meaning in Nvidia's move for acquiring Groq here, but it might just be as simple as, I think it's a cool piece of technology. We are missing it from what we can do. So, here's a price of $20 billion to buy it, because why not? We have the money.
Totally.
Nvidia can do that. Not too many people
They
otherwise.
can. Awesome. Cool. All right. Thank you, Vic. Well, listeners, I hope you liked our first episode. Thanks for listening and stay tuned for the next one.